Quantum decoherence is a funny concept in the world of physics. It's like the cosmic version of when you're trying to take a group photo and someone keeps moving around, causing everyone else to become blurry. In this case, the blurry part is the quantum state of a particle, which becomes mixed with its environment due to interactions. So let's say you have a particle, like an electron or photon, and it's in a quantum state. This means that it's in a superposition of two or more possible states, like being in two places at once or having two different spins at the same time. However, the moment this particle interacts with its environment, such as through collisions or other interactions, the superposition collapses, and the particle ends up in just one of the possible states. This collapse is known as quantum decoherence. Think of it like a game of Jenga. The quantum state is like the tower, and each block represents one of the possible states. As long as the tower is standing, the particle is in a superposition of these states. However, the moment you start pulling out blocks, the tower becomes unstable and eventually collapses into just one state, like the tower falling down. In the same way, the particle's interaction with the environment causes its superposition to collapse into just one state. Now, this may sound like a bummer for quantum physicists who love to study the weirdness of quantum mechanics, but decoherence is actually a crucial part of how the classical world emerges from the quantum world. You see, in the classical world, objects are always in one definite state, like a ball being in a particular location or having a particular velocity. Decoherence helps to explain how this classical behavior arises from the quantum world. By interacting with its environment, a particle's superposition collapses into just one state, which is what we observe in the classical world. But let's not get too serious. Quantum decoherence can also be thought of as the ultimate party pooper. Imagine you're at a quantum party, and everyone is in a superposition of different states, like dancing and sitting at the same time. But then the environment, like a sudden gust of wind or someone turning on the lights, causes everyone to collapse into just one state, like sitting or dancing. The party is over, and everyone is just doing one thing. That's quantum decoherence for you. So, why does quantum decoherence happen? Well, it's because of something called entanglement. When two particles are entangled, their quantum states become linked in a way that the state of one particle affects the state of the other, no matter how far apart they are. This means that if you measure the state of one particle, you'll instantly know the state of the other, even if it's on the other side of the universe. But here's the catch. Entanglement only works if the particles are isolated from their environment. If they interact with their surroundings, like by colliding with other particles or being bombarded by radiation, their entanglement is disrupted, and their states become mixed with their environment. This is the essence of quantum decoherence. It's like trying to keep a secret at a loud party. If you and your friend have a secret handshake, you can use it to communicate without anyone else knowing. But if the party is too loud, and everyone else is shouting and dancing, your communication will be disrupted, and your secret handshake will be useless. In the same way, a particle's entanglement is disrupted by its interaction with its environment, and its quantum state becomes mixed with the surroundings. So, to sum up, quantum decoherence is the process by which a particle's superposition collapses into just one state due to its interaction with its environment, which disrupts its entanglement with other particles. This collapse is what we observe in the classical world, where objects are always in one definite state. However, decoherence also poses a challenge for quantum computing and other quantum technologies, which rely on maintaining and manipulating superpositions of particles. To overcome this challenge, researchers are developing new ways to isolate particles from their environment and preserve their entanglement, such as through the use of quantum error, correction codes, and quantum memories. In conclusion, quantum decoherence is a fundamental concept in quantum mechanics, where a particle's superposition collapses into just one state due to its interaction with its environment, disrupting its entanglement with other particles. While this collapse is what we observe in the classical world, it also poses a challenge for quantum technologies, which rely on maintaining and manipulating superpositions of particles. Nonetheless, quantum decoherence is a fascinating phenomenon that reminds us of the weirdness and unpredictability of the quantum world. So next time you're at a quantum party, remember to keep the environment quiet, or else you might just end up collapsing into one state like a bunch of party poopers.